In question 1, we're given a graph of f, and we want to compute this function value in these limits. So f of -8 is the value of the function at x equals -8, which is y is -3. For the next part, the limit as we approach -2 from the left appears to be the y values are getting closer to 3, and that is the limit. As we approach -2 from the right, it appears that the function is increasing without bound up to positive infinity. The limit as we approach 6 from the left looks like it is approaching, the open circle here is at 2, so that's the value of the limit. If we approach 6 from the right, the y values are getting closer to 5. The limit as we approach -2 altogether, well, it's different on the left than it is the right, and so this limit actually does not exist. And the reason is, the limit as we approach to -2 from the left of this function, we found it was equal to 3, and this can't be equal to the limit as x approaches -2 from the right, which we found to be positive infinity. I mean, it doesn't exist at all. Now, what about the limit as we approach, that's supposed to be a 6 from both sides? And this one does not exist either, so I'll say this does not exist. And again, here we have the limit as x approaches 6 from the left, which is equal to 2, and that's not equal to 5, which is the limit as x approaches 6 from the right. In part A, we cannot solve this limit by direct substitution, that is putting 2 into both of the x's, because you'll get 0 over 0. We can factor this expression, and that's what I'll do first. This is equal to the limit as x approaches 2 of, well, the denominator is a difference of squares, and that's x minus 2 times x plus 2. The numerator is a difference of cubes, and that can factor as well, as x minus 2, and we're going to have a quadratic left over, and the quadratic is x squared plus 2x plus 4. Written this way, we can now cancel the factor of x minus 2, and we're left with the limit as x approaches 2 of x squared plus 2x plus 4 divided by x plus 2. There is no problem with putting 2 in place of all the x's now, and we get 2 squared plus 2 times 2 plus 4, all divided by 2 plus 2. And when we simplify this, we get 12 over 4, or an answer of 3. Here is another limit where you cannot use direct substitution because you'll have a 0 over 0. So for this problem, we're going to use a conjugate. That is, we're going to take the original expression, which is this, and we're going to multiply the top and bottom by, I'm going to look at this term, these two terms, and change this minus to a plus, and write it as root 9 plus x plus 3. And I have to do the same thing to the denominator as well. Now, when I multiply the tops and bottoms, we get the following. This is the limit as x goes to 0 of, I'll do the denominator first. It's x times this thing, and I will not distribute it in. I would like to cancel the x at some point, so I'll just put x times root 9 plus x plus 3. Now, when I multiply these two pieces together, it's first going to be the square root of 9 plus x times the square root of 9 plus x, which means you're squaring this, which leaves you with just 9 plus x. You then get this times this, which is plus 3 times root 9 plus x. We then get negative 3 times this thing, which is negative 3, 9 plus x. And then lastly, we get negative 3 times positive 3, which is negative 9. And the nice thing about this process is the middle terms cancel. And actually, this 9 cancels with this -9. And all that's left over is the x. This is the limit as x goes to 0 of x divided by x times root 9 plus x plus 3. These x's cancel. There's a 1 left over in the numerator. So we have the limit as x goes to 0 of 1 over root 9 plus x plus 3. And if you put 0 now in place of the x, you get this. And this is really the root of 9, square root of 9, which is 3. And 3 plus 3 is 6. The answer is 1 over 6. To figure out this limit, I want to somehow remove this x squared from within the root. So my first step is, this is the limit as x approaches infinity of, if you factor an x squared out of both terms in the numerator, you are left with 4 plus 3 over x squared. And the reason is, if you multiply this back, you get 4x squared. And if you multiply this here, the x squareds cancel, and you'd have just a 3. Then we divide by 1 minus 2x. Now in the numerator, this is the limit as x approaches infinity of, we haven't done a thing to the denominator, but we can break a product of square roots into 2 separate square roots, like this. So we have the square root of this times the square root of this. Now what is the square root of x squared? Just off to the side here. Technically, it's the absolute value of x, meaning it could be positive or negative x, depending on the value of x. Since we are approaching positive infinity, we're going to use the positive solution. So we're going to use plus x as x is approaching infinity. All that means is this whole thing simplifies to positive x. If we were going to negative infinity, we would use negative x. So this is the limit as x goes to infinity of x root 4 plus 3 over x squared, and then 1 minus 2x in the denominator. I'm now going to divide the top and bottom by the x with the greatest exponent in the denominator, which is an x to the first. That means I'm going to divide this whole thing by x, which I'll put here, and I'll divide these two terms by x. We have, this is the limit as x approaches infinity of, so I'll put x over x. So I divide the entire numerator by x, and I can choose to divide to either of these terms. I'll divide it to the x. If I divide the entire denominator by x, I get 1 over x minus 2x over x. These cancel, and so do those. Moving over here, this is the limit as x approaches infinity of the square root of 4 plus 3 over x squared, all divided by 1 over x minus 2. We can now evaluate the limit as x goes to infinity. This goes to 0, and this goes to 0. This will leave us with the square root of 4 plus 0 over 0 minus 2. Or the square root of 4, which is 2, divided by negative 2, and the whole thing is equal to negative 1. In question 3, we have a piecewise defined function, and we want to determine where it is discontinuous and justify our answers. So here's the definition of continuity at a point A. That happens if the limit as x approaches a of the function is equal to f of a. There's really only two numbers to check, 0 and 2. So at x is equal to 0, is this function continuous? What I'm going to do is look at the limit as x approaches 0 from the left of this function and see if it's equal to the limit as x approaches 0 from the right. If they're different, it means the limit does not exist and therefore it is not continuous or discontinuous. If we approach 0 from the left, we're using this portion of the definition, so I'll replace f of x with 1 plus x squared. That is, this is the limit as x approaches 0 of 1 plus x squared. On the other side, since we're approaching 0 from the right, we're using this portion of the definition, which is 5 minus x squared. In both of these, we can put 0 in place of x. So this is 1 plus 0 squared. And this other side is 5 minus 0 squared. Or does 1 equal 25? And the answer is no. So do these things actually equal each other? They do not. So this is enough to say f is discontinuous at x is 0. Now let's check the other number, which is 2. And we'll do it the same way. I'm going to check to see if the limit from the left is equal to the limit from the right. If they're equal, I'll then check to see if it equals the value of the function there. And if any of those things go wrong, we know it is discontinuous. So I want to look at the limit as x approaches 2 from the left of this function and see if it's equal to the limit as x approaches 2 from the right. In our definition of the function f, if we're approaching 2 from the left, we're using this portion of the definition, and so we have 5 minus x squared. And is that equal to the limit as x approaches 2 from the right of, well, here we're using this part of the definition, which is x cubed plus 1. We can put 2 in place of x. Here we get 5 minus 2 squared, which is 3 squared, which is 9. Is that equal to, okay, if I put 2 here, I get 8, and I add 1, I also get 9. So this means the limit actually does exist. Now, is the limit as x approach 2 of this function equal to f of 2? Well, f of 2 is equal to, here, 2 cubed plus 1, which is 9. So this function is continuous at x equals 2. So f is continuous at x is equal to 2. So there's only one number at which this function is discontinuous, and it is x is equal to 0. Now further, it says, identify the discontinuity of the function as removable, infinite, or jump. Since the limit on one side is 1 at 0, and the other side it's 25, this is a jump discontinuity. And that's because there's a break or a jump within the graph instead of just one point being removed. It goes on to say further, can we justify that even though it's not continuous at 0, is it continuous from the left or the right? Now, I'm seeing that there's an equal sign if we're coming in from the left, and we don't have one if we're coming in from the right. So I'm thinking this is continuous from the left, but we need to check this. So is this function continuous from the left? At x equals 0, the answer is yes. So picking up here, if you look at the limit as x approaches 0 from the left of this function, I know that is equal to the limit as x approaches 0 of 1 plus x squared, which we know is 1. But this is also equal to the value of the function at 0. So just on the left side, if we approach 0 from the left, it's equal to the value of the function at 0. And this means f is continuous from the left at x is equal to 0. So essentially, if you know that something is not continuous at a point, you can examine it a little bit more carefully and say, well, what if I just choose one side, either the left or the right? Is it continuous for either of those sides? And for this one, it is from the left. In question 4, part A, we're given the function f of x is equal to 2x plus 2. For any epsilon bigger than 0, we want to find the largest value of delta such that if the absolute value of x plus 1 is less than delta, then the absolute value of f of x is less than epsilon. The way to do this is to start by looking at the absolute value of f of x, and we want this thing to be less than epsilon. Well, f of x is equal to 2x plus 2 in absolute value like this, and you can factor a 2 out from both terms. Here we have the absolute value of a product of 2 and x plus 1. You can split that into the absolute value of 2 times the absolute value of x plus 1, and I don't need the parentheses around it anymore because it's not being multiplied by 2. Now here, the absolute value of 2 is just positive 2, and it's being multiplied to x plus 1. Now, since we want the absolute value of f of x less than epsilon, and this is equal to this, we can say this must be less than epsilon. So I'll say we need a delta such that if the absolute value of x plus 1 is less than delta, then f of x, which equals 2 times the absolute value of x plus 1, must be less than epsilon. Now, we can take this inequality and divide 2 to the other side. So we have now the absolute value of x plus 1 is less than epsilon over 2. Therefore, we will choose delta equaling to epsilon over 2. And the reason for this is when you divide 2 to the other side, you're left with the absolute value of x plus 1, which is this. And there's something on the other side, and that's exactly what we want delta to be equal to. To solve part B, we're going to use the squeeze theorem. We're approaching 1 from the left, and we're going to show that this limit of 7x is going to be equal to the limit of 3x squared plus 4. If these two limits are the same, it forces the function in the middle to have the same limit. It's being squeezed to the same value. So we're going to look at the limit as x approaches 1 from the left of 7x, and well, that's just 7 times 1, which is 7. And if you look at the limit as x approaches 1 from the left of the other equation, which is 3x squared plus 4, you can plug in 1, and you get 3 times 1 squared plus 4, which is also 7. So this thing is going to 7 as we get close to 1 from the left, and so is this. The squeeze theorem says that since this is between these two things, it must have the same limit. So I'll say, by the squeeze theorem, we have the limit as x approaches 1 from the left of f of x is also 7. In question 5, part A, we're going to use the intermediate value theorem. We're given a function f of x is equal to e to the x minus x squared, and we want to show that this equation has a solution equaling 0 on the real line somewhere. The way you use this theorem is by doing a few things. There's a checklist. First, you have to know that this function is going from a negative number to a positive number, and this will allow us to create some interval. Second, you have to know that this function is continuous on that interval. The second you know that, this theorem says it will assume every value between that negative and positive number. And since 0 is between a negative and positive number, this equation has a solution. So first, you have to examine this and think, well, what number could I put in place of x that would give me a negative number back? And I think the first thing that jumps out at me is using -1. If you put -1 into this equation, you have e to the -1, which is a positive number, and you're subtracting 1. I believe that will be negative. And then I'm going to use the number 0 for the other endpoint, because if you put 0 into this equation, e to the 0 is 1, and 1 minus 0 is 1. So it should go from a negative to a positive number over this interval. So first, is f continuous on the interval from -1 to 0? And the answer to this is yes. And the reason is e to the x is continuous, as it's an exponential function, and x squared is continuous. And the difference of continuous functions is continuous. So kind of a long explanation, but e to the x is continuous, x squared is continuous, it's a polynomial. If you subtract them, they're continuous everywhere, and specifically on this interval here. Okay, next, we have to know, well, what's f of -1? And all I care about is that it's a negative number. If I plug this into the function, I get e to the -1 minus -1 squared. This is 1 over e minus 1. Now, e is a number that's bigger than 2. So you could think of this as something as close to a half. And if you have a half and you subtract 1, I don't know the exact value, I suppose, but I do know it is definitely negative. Now, if you check f of 0, that's e to the 0 minus 0 squared, which is 1 minus 0, and that is positive. Therefore, we know that f of 1, -1, is less than 0, is less than f of 0. Our function goes from a negative number to a positive number, and 0 must be in between. We can now say, by the intermediate value theorem, there is a number, which I'll call c, in the interval from -1 to 0, such that f evaluated at this number c is equal to 0, meaning there is a solution to this equation. I want to find all asymptotes of this function f of x, and I'll start with the vertical asymptotes. I'll use a fact. X equals a is a vertical asymptote if, when you evaluate this in the function, you get a non-zero number divided by 0. So if you have 0 over 0, that may or may not be a vertical asymptote, but in a rational function, a non-zero number over 0 will result in a vertical asymptote at that value. Does that happen for this function here? The answer is yes. It happens when x is equal to positive 2. And the reason is, if you put that number into the function, if you evaluate f of 2, you get 3 over 0, which is precisely this. So x equals 2 is a vertical asymptote. Now, what about the horizontal asymptotes? Technically, you have to do two things. You have to look at the limit as x approaches both positive and negative infinity of your function. If either is equal to a number, that is a horizontal asymptote. I know since this is a rational function, there's only going to be one. So I'm actually just going to put a plus minus infinity here because I believe both of these limits will be the same. So I'd like to figure out, well, what is this? To carefully compute this limit, I'm going to divide every term by x. That's the x that has the largest exponent in the denominator. So this is the limit as x approaches plus or minus infinity of x over x plus 1 over x divided by x over x minus 2 over x. Now, if we simplify, this is the limit as x approaches either positive or negative infinity of 1 plus 1 over x divided by 1 minus 2 over x. And written in this way, if you go to either positive or negative infinity, both of these go to 0. and so your expression looks like 1 plus 0 over 1 minus 0, or simply 1. And this means y is equal to 1 is a horizontal asymptote. And these are all the asymptotes on this rational function. To find f prime of x, I'm going to use the limit as h goes to 0 of f of x plus h minus f of x all over h. This is the limit as h goes to 0 of, okay, first I have to put an x plus h into all of the x's. And so I get 2 times x plus h squared plus 6 times x plus h plus 1. And I have to subtract the function. And I have to be careful. I want to subtract the whole function, so I'll use parentheses. So I have 2x squared plus 6x plus 1 all over h. The rest is a matter of simplifying. So to start with, I want to square x plus h. So that's 2 times x squared plus 2xh plus h squared. I'll now distribute in a 6. So I get 6x and 6h, and I have plus 1. If I distribute the negative, I get minus 2x squared minus 6x minus 1. Before we can start canceling stuff, I'm going to distribute in this 2, and we have, this is the limit as h goes to 0 of, so we get 2x squared plus 4xh plus 2h squared plus 6x plus 6h plus 1. Then we have minus 2x squared minus 6x minus 1 all over h. And a lot of stuff should cancel. And it does. Those cancel. And so does this. And this. What is left over is the following. This is the limit as h goes to 0 of, we get 4xh plus 2h squared plus 6h over h. I can now factor an h out from every term in the numerator. And that gives us h times 4x plus 2h plus 6 over h. Those cancel. This is the limit as h goes to 0 of, actually just 4x plus 2h plus 6. If you put 0 into all of the h's, only 4x plus 6 is left over, and that is the answer. From part A, we figured out this, that the derivative was 4x plus 6. I now want to find the slope and the tangent line at x is equal to 3 on the original function. And the original function was f of x is equal to 2x squared plus 6x plus 1. Well, first, if you want the slope of the tangent line, that's actually, by definition, the derivative at 3, which is 4 times 3 plus 6. And so the slope of our tangent line is 12 plus 6, and that is 18. Now, if you want the equation of a tangent line, you can use either y equals mx plus b, or I prefer to use y minus y1 is equal to m times x minus x1. Because we already know our slope, I now just need a point x1, y1. We can use this equation to get it. Essentially, we're saying x1 is equal to 3. If you want to find y1, you put 3 into your original function. That's 2 times 3 squared plus 6 times 3 plus 1. Or y1 is equal to 37. In my formula, I have y minus 37 is equal to 18 times x minus 3. If you want to write this in y equals mx plus b form, we can distribute the 18, and we get 18x minus 54, And then if we add 37 to both sides, we get that y is equal to 18x minus 17. And this is the final answer.